Any questions? I believe we last left off for a charge moving into moving through a magnetic field, the force on that charge. We talked about the fact that a moving charge creates a magnetic field. And also brought up what the right hand is. So, all right, this is going to represent the magnetic field. And which direction is that magnetic field going? People have a chance to catch up, and then I'll ask the question again.
What's the B?
That's the symbol for a magnetic field. That's the letter to use. Okay, so in which direction is that magnetic field moving? Or pointing? What do the dots represent? Think of an arrow. Which way were you pointing?
That way.
That way?
Yeah.
If the magnetic field were pointing that way, then I would have drawn the lines like that. So which way is it pointing here?
Towards the board.
So you're going that way, Jackie, were you about to say something different?
I was gonna say the opposite way.
Going that way.
Wait,
What does an arrow have to do with it?
because if you see I remember you saying like if you see the end of the arrow with the dot, then it's going, I forgot which way you said. It's going,
Think of an arrow.
okay, but the,
You got a point on one end and feathers on the other end. If you're seeing the point, which way is it? Yeah. So the arrows, so this would represent a vector pointing that way. Into this, I'm going to take an electron, I'll start out with a proton, take a proton, and I have a proton shooting into here. Which way will the force be on that proton when it enters the magnetic field?
Same way as the magnetic field.
Oh, like a river, throwing a stick into a river?
Sure.
No, it does not work out that way. All right, so let's go back to the direction of the force will be in the direction of V cross B. So let's talk about cross products. When you're doing a cross product between two vectors, you put your hand in the direction of the first vector, which is V. velocity of that particle is that way. So put my hand in that direction. So I've got basically 360 degrees in which I can have my hand. I want it so that when my fingers bend, they will bend, the non-thumb fingers, they will bend towards the second vector in the quickest way possible. Well, since the second vector is out that way, I need to have my hand like that, so that my fingers bend towards the second vector. My thumb points in the direction of the force, or the cross product. So this will be forced down. If you wish to do it a different way, let's set up a coordinate system here. I hat, J hat, and then K hat coming out at us. This is a right-handed coordinate system because I cross J equals K. In a right-handed coordinate system. I cross J equals K. Matter of fact, in a right-handed coordinate system, what's J cross K? Excuse me? As J cross K would be K? Is that what you're saying? No.
I.
Is that just because it's the letter that's missing?
Yes.
How do you know it's not negative I?
Well, if it's not I, then I was gonna guess negative I.
Ah. Let's narrow it down. Doing a cross product, right hand rule. Put your hand in the direction of the first vector, J. J is up. I want my hand fingers to curl so they point in the direction of the second vector. K is coming out. The cross product. So hands up. And K is coming this way, so I want my fingers to be able to bend in that direction.
I think I finally understand what this is. Not once have I ever understood what this hand means.
And then K cross J.
Negative I.
There would be. Right hand rule, we've got K coming out,
Yeah.
J is going up, so I want my fingers to bend up, my thumb points in the direction,
Okay.
points in that direction.
Okay.
So we can set up I, J, K, and if you go around the corner, I, J. If I'm going in this direction, the I, J, K direction, I'm gonna get it positive. So I cross J is positive K, J cross K is I, K cross I is J. If I go opposite, I get a negative. J cross I is negative K, I cross K is negative J, K cross J is negative I. So, from that point of view, my velocity is in the I hat direction. B, my magnetic field is outwards, which is in the K hat direction. K cross I, sorry, just the opposite, I cross K. Well, I have I and K right there, that's going in the negative direction. That would be negative J. Downwards. So as soon as it, back up again. So if the force being applied is perpendicular to the motion, what's going to happen? I was trying to figure out what your hand gesture meant.
Can you ask that again?
All right, so I have an object moving along to the right, in my case right there. And then the force applied is perpendicular to the motion. What's gonna happen? This could have also been a 151 question. Say it again?
Will it be like, I don't know how to explain it. Will it like how in some of our others, when one thing is perpendicular to another, it will equal 0?
Oh, if you're doing a dot product.
Okay, but it's a cross product.
Yeah, we're not doing a dot product here. What is Newton's first law of motion?
Is it an object in motion will stay in motion unless acted upon by another force?
Yeah, pretty much. Not only will stay in motion, but wants to maintain velocity. So here I have a force acting on it. I guess I should actually label that. So that is a force. And that is velocity. Or Newton's second law of motion. It's the formula one. What I labeled at the time, and the null is the only one who potentially has an excuse here, what I labeled as the most important equation in physics. Times like these, I'm thinking, man, I need an impact. F equals,
MA.
thank you. So if I have only one force acting on this particle, that's the force from the magnetic field. Since F equals ma, Newton's second law of motion, then the acceleration must be in that direction. So I have an acceleration that is perpendicular to the velocity. What kind of acceleration is that? What is acceleration? Or when is there acceleration? All of you should know this one. Physics 151, chapter 2 and 3, and periodically throughout the rest of the book.
It's the change in velocity.
All right, officially, yeah, if there's a change in velocity, there is acceleration. Acceleration is, let's do for completeness, it's related to change in velocity. So, looking for the full formula. I think you just said it.
Oh, yeah. Over to.
All right. All right, so if there's a change in velocity, there's acceleration. If there's a net force, that's not zero. If I have an unbalanced force acting on an object, there will be acceleration, therefore change in velocity. What are the three ways velocity can change? Or, look at it from this point of view, from a physics point of view, if you are driving an automatic transmission, what are the three accelerators you have easy access to? Three things that will change velocity.
Gas pedal. Gas pedal.
Okay, there's one.
Brake pedal.
Two. And what's the thing you have? Yeah.
Okay. Or reverse.
Yeah, I was trying to keep it simpler than that. All right, so we got three things. Actually, if you're going in one direction and one to reverse, I would recommend braking first instead of just throwing it in
Yeah,
reverse.
that'd be.
You do. So if there's acceleration, that means it's gonna speed up, slow down, or change direction. Well, I know if I get pushed in the direction I'm moving, I'm gonna speed up. If I push opposite the direction I'm moving, I'm gonna slow down. But if I push perpendicular to the way I'm moving, what's gonna happen?
You're gonna change direction.
Yeah. And as soon as I change direction there, well, that my velocity direction is changed. My magnetic field's still the same, so let's say that a moment later I'm going in this direction. What's the direction of the force? Yeah, if that red line there, or red arrow is my velocity vector, what would be the direction of the force?
Would still be down.
It will not. Can you point in the direction it's going to go? So the force is in the same direction?
Is it gonna be perpendicular going that way?
Yeah. Cross product always going to produce a perpendicular vector. So my force will be, well, V is that way, V is out. My force is going to be that way. Matter of fact, my force is going to be perpendicular to my motion the entire time. That's in the magnetic field. So if it's constantly changing direction, it's not speeding up or slowing down, it's changing direction. So if it is changing direction, because of a force constantly pointed towards the center, what kind of motion is it? Chapter 6.
Wait, can you repeat what you just said?
All right, so as it moves in here, the force is always going to be perpendicular to the velocity. Because I've got a cross product here, and the product of a cross product is always a vector perpendicular to both of those. So if my force is perpendicular to the motion the entire time, that means it's not going to speed up or slow down, it's constantly going to change direction. What is that motion called? Not speeding up, slowing down, all it's doing is changing direction. Or what will the path look like?
Wanna go in a circle?
Yes. So if you have an object traveling in a circle,
Angular velocity.
there would be an angular velocity, not the words I was looking for.
Centripetal.
That's the one. It is a centripetal motion problem. So if this is 1.6, if Q, 1.6 times 10 to the negative 19th coulombs, which I hope you would know. But take the engineering approach and figure out, you know where to look it up. And the velocity, why don't we make 3 times 10 to the 6th meters per second. The magnetic field, we will make 0.075 Tesla. What will be the radius of curvature? I know that if I increase the magnetic field, let me back to one thing for a moment there. Oh, we'll see where we get there. All right. Initially going in the I-hat direction, perpendicular to the magnetic field, it is going to curve downwards, or at least in that direction. And the question is, what's the radius of curvature? So let's do our classic facades method. Force diagram. I would just take the forces as it's entering the magnetic field. What are the forces acting on the proton? What are the only significant forces acting on a proton? Go for it.
Wait. No.
That's not significant.
I didn't think so.
Yeah, that's gonna be in the order of 10 to the negative 20th meters. Even in my dissertation, we ignored that.
The magnetic field.
Yeah, the force from the magnetic field, the one that we are sort of talking about right now in this chapter. All right, so that is this way. So I'm gonna put F sub B for magnetic field. Although they might be confused with buoyancy, but within context, I'm gonna use D. That's it. And so now, the direction that it will accelerate.
Well, it's
That way. Okay.
At that moment,
Oh.
at that moment, what's the direction of acceleration?
That.
Nope.
No. That way.
Is that up or down?
Down.
It's down. It has to be in the direction of the force.
Okay.
The acceleration is gonna be in that direction. Whatever the direction of the force is. I have one force, the acceleration has to be in that direction. So coordinate axes, I'm just gonna go ahead and make that the positive direction. Do I have to break this vector up? No. It's in the direction of my positive direction, so I'm good there. So decomposition is done. Equations of motion. Remember that when doing equations of motion, this is our template. The force is the magnetic force. That's the mass of the proton, and my acceleration, it's centrifugal.